Hey, here's a freebie for you. For this example, we are trying to find the potential function for the following vector field in 3 space. So we have this 2xy in the I direction, this x squared plus z squared in the j direction, and this 2yz in the k direction. Now remember, to find out if we can find a potential function, the first thing we have to do is we have to find the curl. And we have that rule right here. It's m, n, and p. So our rule says we're going to take the partial of p, you might remember this right here, the partial of p with respect to z, with respect to y, minus the partial of n with respect to z, I minus the partial of p with respect to x, minus the partial of n with respect to z in the j direction, plus the partial of n with respect to x, minus the partial of m with respect to y in the k direction. So we can do that real quickly here. So we're going to take the partial of p with respect to y, so that's just going to become 2z, minus the partial of n with respect to z, 2z. So far we're on the right boat, that's 0, yes, minus the partial of p with respect to x, well that's just 0, the partial of m with respect to z, well, that's 0, oops, so far so good, plus the partial of n with respect to x, 2x, the partial of m with respect to y, also 2x in the k. So this does equal 0, so therefore this is indeed conservative. So now we got to go about and solving this. So let's go a little bit slower than we did in the other video. So I'm going to start with my first term. Remember, this is the partial of my function with respect to x. So when I integrate this to get my function f of x, y, z, this is going to become 2xy dx, because that's the derivative with respect to x. And of course that's pretty easy. This just becomes x squared y plus my constant, which remember is now, since I'm taking the derivative with respect to x here, my constants are going to be in terms of y and z. So now I have to find this yz. So let's see here. To get that, I am going to look at the y's here. So I'm going to go and solve for the y. So what's this telling me to do? From my function, I can take the derivative of my function with respect to y, and that's going to equal from my vector field, its derivative with respect to y. So I know that this is going to equal, with respect to y, that's this one, x squared plus z squared. So when I take my derivative with respect to y, I'm going to get x squared plus c prime of y z, and that's going to equal x squared plus z squared. The x squareds cancel out, and I can actually solve this. Remember, I'm integrating with respect to y, so we're going to integrate this with respect to y, z squared dy, and that's going to give me c of yz equals z squared y. Plus, I'm going to be left with another constant, but this time my constant's now in terms of z, right there. So far, now my function is the following: f of x, y, z equals, where is it at? There it is, x squared y plus z squared y plus c of z. And now I have to solve for z, so I'm now going to take the derivative of my function with respect to z. And I can do that real quickly. That's just 0. Here we get 2zy plus c prime of z. But what is that going to equal? Well, that's going to equal the z component of my vector field, this 2yz up here. 2yz, and of course those cancel out, and we get c prime of z equals 0. And when we integrate 0 dz, we just get our constant. So we get c of z is just a constant. So now I write out my function. F of x, y, z equals x squared y plus c squared y plus my constant. And there is our potential function. To get the actual value, we just have to plug in a point. We did that last year in single variable calculus. Hope you enjoyed this freebie. I'll see you later. Bye-bye.